This is a respiratory system tutorial presented by the SHL TV with reference Color Atlas of Physiology by Agamemnon de Bazouros and Stefan Silbernack. So, you start with respiration. So, you start with the first diagram on the gas transport. So, the first point is that you need to know that anytime everything involving respiration are based on inspiration and expiration. So now, the first point is that the inspired air which enters in our body has a certain partial pressure, and the partial pressure or total partial pressure of that inspired air is 101.3 kilopascals. So now, that 101.3 kilopascal is going to be divided according to each of the different molecules or atoms which are present inside the air. We know that air is made up of 21% of oxygen, 0.03% of 0.03% of carbon dioxide, and is also made up of 79% of nitrogen and 1% of noble gases. Now, each of these percentage are actually called the molar gas fraction. Each of these percentages are actually the molar gas fractions. So now the point is that according to the Dalton's law, we need to know that what Dalton stated that the partial pressure of each of these gases is going to be the mole fraction times the total pressure that these gases are going to exert. Since this total pressure is 101, you are going to multiply each of the partial pressures, which are 0.21 in case of oxygen and for carbon dioxide 0.003 times this each. So you are going to now have the different partial pressures of each of the molecules. So oxygen is going to have 21.17 kilopascals, carbon dioxide is going to have 0.03, and that of this one, nitrogen is going to have 80.1 kilopascals. So now when air is inspired, the next point is that it's going to enter into our alveoli. When air enters the alveoli, after that, the oxygen is going to enter into the blood and be transported at a rate of 0.3 liters per minute. Then you are going to have the cardiac output. It's going to be know that the rate of transport of blood is going to be the cardiac output, which is 6 liters per minute. And then the next point is that inside the arteries, the blood that is transported by arteries, oxygen partial pressure is 12.666. Carbon dioxide partial pressure is 5.27, and that of water is 6.27. The pressure inside the artery is going to be 12.66 for oxygen, for carbon dioxide is that, and for water more is that. So now let's go now to you need to know that this carbon dioxide, oxygen, and then inside the tissues, the pressure of oxygen is going to be 5.30, so it reduces. Carbon dioxide increases to 6.0 and water increases to 6.27. Then we move again up to the veins. In the veins, it's going to be 5.33 for oxygen. For carbon dioxide, it's going to be 6.0. And then for water, it's going to be 6.27. And now when it moves out to the lungs, inside the lungs, it's going to move into alveoli, into the alveoli. In the alveoli, you need to know that oxygen is going to be 13.3 as partial pressure. Partial pressure of carbon dioxide is going to be 5.2. Partial pressure of water is going to be 6.27, and that of high nitrogen is going to be 76.5, and it's going to be expired. The partial pressure of oxygen is going to be expired is 15.33. Partial pressure of carbon dioxide is 4.43. Partial pressure of water is 6.27, and partial pressure of nitrogen is going to be 75.33 kilopascals. So these are the different points. And now, next part now is to see how respiration occurs in the human body. So, point number one, we need to know that the main muscle involved in respiration is the diaphragm. Now, you can have other accessory muscles of respiration, like the internal intercostal muscle and the external intercostal muscle. These are accessory muscles of respiration, but the main muscle is the diaphragm. Now, anytime that you want to visualize the mechanics of muscle respiration, the first point to put in mind is to know the principle of action-reaction forces. Example: you are seated on your chair. example. So this is a typical example. You are seated on your chair. Now if you decide to push the table in front of you, you realize that the table is going to move. Now the point is, why is the table moving while the table is also exerting an equal but opposite reaction force to you? You need to know that when you are exerting the force on your table, the table is also exerting an equal but opposite reaction force to you. But why is that the table is moving and you are not moving? So this is because you are much more stable than the table. If you do this experiment in cases where you have a chair which has rollers underneath, you realize that when you push the table, you are also moving backward because the table is also exerting a force opposite to you. So now, I wish you to understand now the point of action reaction forces at the level of the rib cage. You need to know that what the thoracic cage is made up of the ribs, the sternum, and is also made up of the vertebral column. The thoracic cage is made up of the ribs, the sternum, and the vertebral column. Of all these parts, the most stable part is going to be the vertebral column. The most rigid part or the non-movable part is going to be the vertebral column. So the point to note is that all the ribs is going to move with respect to the vertebral column and not the contrary. So are you getting the point? The ribs are going to move with respect to the vertebral column and not the contrary. So now you need to know that what the external intercostal muscle from the anatomy you're going to visualize that external intercostal muscle are oriented from up to down, while the internal intercostal muscle are oriented from down to up. So now, since the ribs move with respect to the vertebral column, you realize that they are going to have a movement. So when you have a push from Z to Y, there is an equal but opposite push on in the direction YZ. But now you see that it is impossible for the rib cage to cause a movement on the vertebral column. So the resultant force of this system is going to be in the direction ZY. This is why external intercostal muscle is going to cause elevation of the ribs. And now internal intercostal muscle, since they are oriented in this direction, you see that there is a push from the vertebral column. So from in YZ direction, this is the action force, and there's an equal but opposite reaction force in the ZY direction. But it is the vertebral column is much more stable than the rib cage. That's why the ribs are going to move toward the vertebral column, and you realize that this direction is going to take place from Y to Z, and this direction is expiration, the fall of the rib cage. So that's the mechanics involved with respiratory muscle. Now let's visualize the pressures inside the lung and inside and inside the pleural space during inspiration and expiration. So during inspiration, you need to know that the volume inside the lungs increases to about 250 milliliters. Then, and during expiration, you have also a loss of volume of 250 milliliters. The total volume which is being inspired and expired is going to be the tidal volume during normal inspiration and expiration, or during normal breathing. And this tidal volume is a 250 milliliters plus 250 milliliters, that is 500 milliliters. So the tidal volume is usually equals to 500 milliliters. Now during inspiration, what do you realize? The pressure in the alveoli is going to decrease during inspiration. The pressure in the alveoli is going to decrease such that air is going to enter. The pressure in the atmospheric air is going to be higher than the pressure inside the alveoli, such that there is a push of air into the lungs. While during expiration, the pressure in the alveoli is going to increase in order to cause the pressure inside the alveoli to be more than expiratory air, and then push air outward. Now you need to know that increase and decrease pressure in alveoli is a consequence of the increase and decrease pressure in the pleural space. This, you need to know that what the surface tension of the pleural space causes this pleural space to always have a negative pressure with respect to the atmospheric pressure. So that's why, as you can see from this diagram, the pressure of the alveoli are always negative. The pressure of the pleural space is always negative compared to the atmospheric pressure. here you see that there are certain points for alveolar pressure where it's going to be equal, but for pleural pressure is always negative. So you need to know that during inspiration it becomes again more negative and pulls the lungs toward its side and expand the lung. But now during expiration it becomes again more positive. It becomes toward -4, while during inspiration it comes toward -6 centimeters of water. So now let's visualize artificial respiration. You need to know artificial respiration is only a method like that with an oximeter. You have fresh air, oxygen entering, and then enters. And now you have valves at this point to prevent expired air to enter the system. So what happens is that, and this is the pump. So at this position you have expiration that occur here. You have another artificial respiration method, which is the rescue bed, mouth-to-mouth resuscitation, and then you have this other, the negative pressure respiration, where you have both inspiration and expiration after taking control of the respiratory rhythm of the human body. Now let's visualize pneumothorax. Pneumothorax, this is normal lungs first. During inspiration air enters and during expiration air comes out. So pneumothorax, you have two main types of pneumothorax. You have open pneumothorax, and we have valvular pneumothorax. So open pneumothorax, this space here where you have a problem, air actually you have it is entering and it can go out. So this one is not too detrimental. While in valvular pneumothorax, air can enter but air cannot move out. So this is a big problem, a life-threatening complication. So what happens here is that air enters, there's a push, is going to compress this lung, and this lung is going to, you need to know that according to the law that the formula delta P, or the change in pressure, is equals to the two surface tension divided by radius. You see that this volume of lungs is going to be lesser compared to this volume, so the pressure here is going to be higher compared to here. So during expiration, the pressure inspiration, air is going to enter in this, and then during expiration, air is going to enter here and move out here. But now when it's perforated, there is a prevention of expiration, so this lung is going to completely collapse, and it's a life-threatening condition. So now let's have certain definition of lung volumes and their measurement. So we have the residual volume, we have the functional residual volume, the residual capacity, we have the vital capacity, the total lung capacity, and we have the tidal volume. So now let's start definition. So as you can see from this graph, the tidal volume is calculated from this point to this point. The expiratory reserve volume is calculated from this point here to this point here. The residual volume is calculated from this point here to this point here. Now the inspiratory reserve volume is calculated from this point here to this point here. The vital capacity is calculated from this point here to up here. The total lung capacity is calculated for all the lungs from this here to down this position here, and the functional residual capacity is going to be calculated from here to here. So now let's try to derive the definition of each of these volumes. So we'll start with the tidal volume. What's the tidal volume? As you can see from this diagram, you can easily define tidal volume as being the volume of air that is going to be inspired and expired during a normal breathing. The volume of air that is going to be inspired and expired during a normal breathing, and it is usually 0.5 liter or 500 milliliters. That's the first point. Now let's define expiratory reserve volume. The expiratory reserve volume, since it starts from year to year, is going to be defined as the volume of air which is forcefully expired, the volume of air which is forcefully expired after a normal expiration. So you see that here there is expiration that has occurred. Now there is a forceful expiration. So it is defined as the volume of air which is forcefully expired after a normal expiration. Now let's define, and it is usually 1.7 liter or 1700 milliliters. So now let's define inspiratory reserve volume. Inspiratory reserve volume starts from here and goes up here. So now it's going to be defined as the volume of air that is going to be inspired after a normal inspiration. So you see that here, moving up here you have inspiration, moving down you have expiration. Since you first move up before you have forceful, or you have now the definition as the volume of air which is forcefully inspired after a normal inspiration. That's inspiratory reserve volume, and it is usually 3 liters. That is 3,000 milliliters. Now the next point is a vital capacity. Since the vital capacity starts from year to year, so you need to say that what the person is going to forcefully inspire. So the person needs to the person needs to normally inspire, then forcefully inspire, and then expire in order to have this total vital capacity. So now let's define vital capacity. The vital capacity is defined as the volume of air which can be forcefully expired after a normal inspiration and a forceful inspiration. So, or you can easily define as the volume of air which can be forcefully expired after a forceful inspiration. That's the vital capacity. And the vital capacity is usually the formula is expiratory reserve volume plus tidal volume plus inspiratory reserve volume. So that is 1.3 plus 0.5 plus 3 is going to give you your answer. Now you have functional residual capacity. Functional residual capacity, see that it is from year to year. So at this position here, you see that there is expiration. So functional residual capacity, the formula is going to be given as expiratory reserve volume plus the residual volume. So now let's define first the residual volume before define the functional reserve capacity. The residual volume, you see that it is the volume here is from here to this point. So you have completely expired. So what is the residual volume? Residual volume is defined as a volume of air left in the lungs. The volume of air left in the lungs after it's from here to this point and there is forceful expiration already. So it's going to be defined as the residual volume is a volume of air left in the lungs after forceful expiration. The volume of air left in the lungs after forceful expiration. Now let's define functional residual capacity. So you see that and it is the residual capacity usually 1.3 liters. So the total volume of air inside the lungs, which is functional residual capacity, is going to be 1.3 expiratory reserve volume plus residual volume 1.3 plus 1.7, and that gives you 2 liters. So that's how to calculate. So now that gives you 3 liters instead. So now let's point now the total definition. So now what is the total definition? The total definition of functional residual capacity is that functional residual capacity is the volume of air inside the lungs after a volume of air inside the lung after a normal expiration. The volume of air left inside the lungs after a normal expiration. The volume of air left inside the lung after a normal expiration is usually 3 liters. So now let's see the next point. So now you need to know that what since this residual volume is not capable of being calculated, it's also called a dead space. So you need to know that what you need to know that you are not capable of calculating this volume here by spirometry. All these other volumes are capable of being calculated by a spirometer, and this is spirometer here. You can expire the air, inspire the air, and all that is going to be shown by different pressures on this spirometer to know the volume that you have expired and inspired. But the residual capacity is not capable of being calculated. So now let's visualize certain measurements that can be used in order to calculate the dead space. So in order for you to calculate the dead space, you need to first know that what the alveolar volume. So you need to know that the carbon dioxide volume that is going to be expired, the carbon dioxide volume, or that is going to be expired, or the number of moles of carbon dioxide that is going to be expired is going to be the number of moles that is going to be present inside the dead space plus the number of moles that is going to be present inside. So it's a number of moles that is going to be found in expired air is going to be the number of moles that is going to be inside alveolar space, and plus the number of moles present inside the dead space. So number of moles, know that what number of moles equals to the concentration times the volume. So the volume times a fraction, each of these fractions are going to be taken as a concentration, the fractions of each of carbon dioxide in the air. So you have volume times the fraction of carbon dioxide in the volume of the alveoli, the fraction of carbon dioxide in the alveoli, plus the volume of the dead space times the fraction of carbon dioxide in the dead space is going to be equals to volume the tidal volume, which is the expired volume. Is going to be a tidal volume, that is a fraction in expired air. So now, after having this, we need to know that what the volume inside the alveoli actually is going to be equal to the tidal volume minus the dead space volume. And you need to know also that the fraction of carbon dioxide in the dead space is going to be equal to 0, because in the dead space there is no perfusion, so there is going to be equal to 0, the fraction of carbon dioxide there. So now when you substitute everything by substituting VA is going to be that inside this and putting this to be 0, you see that this is going to be equal to this, and then you are going to have the dead space as being equal to this. When you have this dead space being equal to this, you can now say that you can now substitute different value of the tidal volume, fractional this, and then the different fraction. You have the fraction of alveoli, of carbon dioxide alveoli, fraction of carbon dioxide expired, and fraction of carbon dioxide is alveoli. When you substitute every value, you are going to have your dead space as being 143 milliliters. Now this dead space is actually the volume of blood, the volume of the dead space actually is the residual volume is different from the dead space. And what is the dead space? The dead space is actually the volume of air that is going to be present inside the lungs in order to prevent the lungs to collapse. Is the volume of air that is present inside the lungs in order to prevent the lungs to collapse. So that's the point. So now another measurement method to calculate the dead space is by using helium. You need to know that what the number of moles, when you place helium, you have helium here having a certain number of moles, and when now you enter it into the lungs, your helium is going to take the different the volume of the lungs. So now you see the number of moles of the helium in the spirometer here is going to be the number of moles of helium both in the spirometer and inside the lungs, and that number of moles is going to be the volume of the spirometer times the fraction of the concentration of the fraction of the helium inside the spirometer is going to be equal to both the volume of the spirometer plus the volume of the lungs times the fraction of the spirometer at this point. So that's the number of mole. When you have this, you can calculate, and you are going to have your final formula. L, which is the volume of the lungs that you want to calculate, can be given as VSP, volume of the spirometer, all times the fraction of helium in the zero state, where it's only found in the spirometer, and when you have it when it's diffuse associate. So now the next point now that you are going to see are going to be certain work involved with the lungs and inspiration. So you need to know that what you have static compliance. You need to know that when the lungs expand, when you have inspiration, it's going to respect the certain law. You have a graph of volume against pressure. You need to know that it's going to expand ideally. The lungs expand ideally as shown here, but it is actually expanding as this method. So the ideal expansion of the lung is that it expands as such. And now the change in volume, you realize that the volume is it respects a straight line, and now this straight line is going to have a certain plateau. The plateau here is because of the lung recoil, the prevention of the lung to continuously expand due to the elasticity or the elastic recoil of the lungs according to Hooke's law. So now you can now calculate a certain compliance as being equal to the change of volume of the lungs divided by change of pressure at the level of the alveoli. So now you have the next one, which is dynamic pressure of the pressure volume curve. So in the dynamic pressure volume curve is the actual volume of the lungs, the actual volume pressure curve that the lungs is going to move. You need to know that what during inspiration, this is actually an active movement, while during expiration is passive. Inspiration, usually we say that inspiration is active, that is uses energy, while expiration is passive, and it can be shown from this diagram. So what do you realize? You realize that when you inspire, it moves as such here, and when you expire, it descends here. So the point is that, so you see that expiration is going to the total energy that is going to be found here is going to be the loss of energy during expiration. So that's the difference. If it was actually moving with this straight line, the both inspiration and expiration are going to have the same work. But now you see that inspiration has a different direction from expiration. So in that difference is going to be the difference in work performed in inspiration and expiration. The expiration work is going to be lesser compared to that of inspiration. So now let's visualize the next one, surface tension. In this part, I just want you to visualize the formula of surface tension to be the change in pressure. The pressure, the difference in pressure is going to be 2 surface tension. This is surface tension. This gamma is surface tension all over R. So that's the formula I want you to know. And this formula now can be used in order for you to know the different problems inside the lung. So I want you to have different pathologies inside the lung. You have two main pathogens inside the lungs. You have obstructive lung disease and you have restrictive lung disease. So now, and you have a normal lung. This obstructive and restrictive lung disease are capable of being calculated by the pulmonary ratio. So now the fractional ratio, or so now this fractional ratio actually is the forced expiratory volume in 1 second divided by the forced vital capacity. You know that in obstructive lung disease, you have the ability of the lungs to contain air is going to be high, but the ability to expire is going to be low. So if you take the forced expiratory volume divided by the forced vital capacity, which is the capacity of the lungs to contain air, you are going to see that for obstructive lung disease, the value is going to be lower. So as you can see here, you have 0.4. The value is going to be lower for obstructive lung disease. Now we see that in cases of restrictive lung disease, the ability to expire is increased and the forced vital capacity is going to be low. So in restrictive lung disease, you are going to have a greater forced expiratory volume, and you have a lesser forced vital capacity. The expiratory volume is 0.8 and the forced vital capacity is 0.4. So when you do 0.8 divided by 0.4, you are going to have a certain value. And therefore, obstructive lung disease, the ability to the forced expiratory volume is going to be low, 0.4. While in the case of forced vital capacity is going to be high, 0.8, and then you are going to calculate. You see that it's going to give you the pulmonary ratio here is going to be smaller, while the pulmonary ratio here is going to be larger. The pulmonary ratio is going to be defined as the forced expiratory volume in 1 second divided by the forced vital capacity. And lastly, we have the combined lung disease, which is the intermediate between obstructive and restrictive lung disease. So now, alveolar gas exchange. So this is alveolar gas exchange. The partial pressure of carbon dioxide is going to move our oxygen to enter into the red blood cell and then move as such. So now we need to know that the different parts of the lungs are going to have different perfusion and different ventilation. So there are certain parts in the lungs that have normal ventilation and we have equal ventilation to perfusion. There are certain parts where the perfusion is going to be lower than the ventilation. There are certain parts where the perfusion is the ventilation is lower than the perfusion, and there are other parts where you have a membrane preventing ventilation. So all that are going to be known. So now let's study now the ventilation perfusion ratio. So we need to know that at the apex of the lungs, there is much more ventilation compared to perfusion than at the middle part of the lungs and than the lower part of the lungs. So let's visualize this. So we need to know that as you can see here, the alveolus is found here. Do you see that the arches that come are going to have less? You see that there is much more resistance at this point, so less perfusion. The resistance is going to milder here, and there is low resistance at this point, so perfusion is going to be greater at this position here. So now let's see the graphs of perfusion as you move from apex to the base of the lungs. The graph of perfusion and ventilation as you move from apex to the base of the lungs. So now you need to know that ventilation is going to be shown by this orange line, while perfusion is going to be shown by this red line. So you see that at the apex of the lungs, actually perfusion, you see that ventilation increases as we descend, we go to the base of the lung. Ventilation increases as we descend to the base of the lung. is quite right. Also, perfusion increases as we move to the base of the lungs. But now, the point is that when calculating the ventilation perfusion ratio, you see that as you move from the apex to the base, is going to decrease, and as you move from the base to the apex, the ventilation perfusion ratio is going to increase. And the reason is just because since the ventilation at the apex is going to be more than perfusion. Since ventilation is more than perfusion and the ventilation perfusion ratio is ventilation over perfusion, you are going to have higher ventilation perfusion ratio at the apex compared to the base, where the perfusion is going to be greater than the ventilation, and you have a lower perfusion ratio, lower ventilation perfusion ratio. So now let's visualize the different cases here. So we have different points. Let's say that your ventilation perfusion ratio is 0. When the ventilation perfusion ratio is 0, you realize that what the pressure of carbon dioxide is when the ventilation perfusion ratio is 0. What does it mean? It means that this is not going to be ventilated. So just imagine having ventilation perfusion ratio to be 0. When ventilation perfusion ratio is 0, it means that the ventilation is 0. 0 divided by any number gives 0. So it implies that this alveoli is not going to be ventilated. That's the conclusion. Since this alveoli is not going to be ventilated, so it implies that what there is extremely high perfusion in this alveoli, but there is no ventilation. So here you are going to see that the partial pressure of oxygen is going to be very small, while the partial pressure of carbon dioxide is going to be very large for this not ventilated alveoli. So now in normal alveoli, we are having this partial pressure of 13.33 as you have seen in the introduction, and partial pressure of carbon dioxide of 5.33 in normal, when the ventilation perfusion ratio is going to be 1. So, and now when it is not perfused, totally, you are going to see that the value of this cure is actually 0. When you have any number divided by 0, you are going to have infinity. Any number divided by 0 gives infinity. So when the value of the ventilation perfusion ratio is extremely large, you are going to say that perfusion is, when the value is infinity, then you are going to say that this perfusion is going to be 0. This is not perfused. Since it's not perfused, it means that the blood does not pass here, so carbon dioxide cannot be diffused into alveoli. That is why the partial pressure of carbon dioxide is 0, and the partial pressure of oxygen is going to be extremely large at this position here. So now let's visualize how the fraction of lung volume changes. So you see that at this position here, the lung volume at the apex is going to be small, 0.07, while the lung volume at the base is going to be larger, 0.13. Now the ventilation rate. Ventilation at the level of the apex is smaller compared to ventilation at the level of the base, and perfusion at the level of apex also smaller than the level of the base. But when you calculate the ventilation perfusion ratio as here, you see that ventilation perfusion ratio at the apex is going to be larger compared to base, meaning that at the apex there is going to be much more ventilation compared to perfusion, while at the base is much more perfusion compared to ventilation, and at the middle you have approximately equals to 1. Then you have the partial pressure of oxygen. What does it mean? So since this part here is going to be having more ventilation compared to perfusion, you see that there is going to be much more oxygen at this position and less carbon dioxide. This is why the partial pressure of oxygen is 17.6 and the partial pressure of carbon dioxide is 3.7. And at the middle you have this. Now at the base, since the base is much more perfused than ventilated, you are going to see that the partial pressure of oxygen at the base is going to be lower compared to that of carbon dioxide. So carbon dioxide partial pressure is going to be high, and the partial pressure of oxygen is going to be lower at these positions here. So now we have the carbon dioxide transport in blood. So let's visualize it. So you first start inside the tissue. So inside the tissue we have carbon dioxide. So when you have this carbon dioxide, you realize that there are different methods of transport of carbon dioxide. Number one method of transport, the main method of transport of carbon dioxide is via hydrogen carbonate inside the blood plasma. So carbon dioxide can penetrate inside the red blood cell, and carbon dioxide is acted by carbonic anhydrase, which convert it to hydrogen carbonate. So it converts to hydrogen carbonate by addition of water molecule and the loss of hydrogen ion. And now this hydrogen ion now can be bounded to oxyhemoglobin to be stored inside the red blood cell as being hemoglobinic acid. This is hemoglobinic acid here. So this is carbonic anhydrase. The carbonic anhydrase now can be lost into the plasma and then enters now into other red blood cells now for the. So we have the next position here. We have hemoglobinic acid. So now after having the carbon dioxide being transported in blood via hydrogen carbonate, you're going to move inside the blood via the chloride ion shift with this chloride ion hydrogen carbonate ion antiporter. So now let's visualize oxygen. So you need to know that at the level of the tissue, oxyhemoglobin is going to break down to produce oxygen in two forms. The first form is that oxyhemoglobin is going to bind with one molecule of hydrogen ion coming from carbonic anhydrase to produce hemoglobinic acid, and it's also going to bind with hydrogen coming from there's also going to be a release of this hydrogen ion in oxyhemoglobin when oxyhemoglobin binds with carbon dioxide to produce carbaminohemoglobin or hemoglobin carbamate. So the oxygen is going to be lost here and going to move to the tissue. So we have the next point now. Hydrogen at the level of the lungs, you see that the hydrogen carbon is going to be transported in the plasma. At the level of the lungs, hydrogen carbonate is going to enter into the red blood cells via the chloride ion shift, and now hydrogen carbon is going to bind again with one molecule of hydrogen ion, and is going to release water and carbon dioxide. Now the carbon dioxide can move out to and expel inside the alveoli out from the lungs. So now the next part is that this hemoglobin that you have seen here, hemoglobinic acid, are the one now involved in releasing hydrogen ion at the level of the lungs. So now the next point is that we have oxygen. Oxygen here is going to bind. Oxygen is going to enter at level of the alveolus. Oxygen is going to enter from the alveolus into the red blood cell. Inside the red blood cell, they are going to bind with hemoglobin and one molecule of hydrogen ion to form oxyhemoglobin. So that's how it binds, and with that oxyhemoglobin is going to have you are going to have the loss of carbon dioxide from that hemoglobin carbamate that we had down here, and now it's going to be expelled from the lungs. So that is the transport of oxygen and carbon dioxide all through the bloods. So now the next thing is to see the effect of carbon dioxide on the pH. We need to point out the fact that hydrogen carbonate is not soluble inside the cerebrospinal fluid. So we need to know effect of carbon dioxide on pH inside the cerebrospinal fluid. We need to know hydrogen carbonate is not soluble, is not diffusible through the blood-brain barrier, so it does not enter the cerebrospinal fluid. So what enters the cerebrospinal fluid is actually carbon dioxide. So if you have an increased carbon dioxide level, what happens is that you are going to have a rapid diffusion through the blood-brain barrier, which is going to increase carbon dioxide level inside the cerebrospinal fluid. Now, carbon dioxide is going to bind with water molecule to produce hydrogen ion and hydrogen carbonate now inside the cerebrospinal fluid, and the hydrogen ion is what is going to account for a decreased pH inside the cerebrospinal fluid. The decreased pH inside the cerebrospinal fluid now is going to affect the central chemoreceptors, so the respiratory centers of inside the brain, and now this is going to cause a strong signal for respiratory regulation. And in this case, where you have increased carbon dioxide in blood, you are going to have a hyperventilation and you are going to have a prolonged expiration. So those are the points. So the next thing is when you have a chronic problem. Let's say that you have a chronic, so in this case it's acute, but now when it's chronic, what's happening is that the hydrogen carbon is going to be higher at the level of the cerebrospinal fluid, because there is going to be slow diffusion. In this case of acute, there was actually no diffusion from blood into cerebrospinal fluid, but now since it's chronic, there's extremely high level of hydrogen carbon, so there's going to be slow diffusion inside through the blood-brain barrier. So hydrogen carbon is going to be also large inside the cerebrospinal fluid. Also, carbon dioxide is going to be large. But now, carbon dioxide, since hydrogen carbonate is also large inside cerebrospinal fluid, the conversion from this position to this position, you see that the equilibrium position is not going to be actually very clear. So thus you are going to have a reduction in the level of the hydrogen, and that's going to be as compared to the acute phase. So the pH here is not going to be as low as in acute phase. So the central chemoreceptors are going to have a weak signal of respiratory stimulation. So now the next point to visualize here is going to be the oxygen dissociation curve. So we have the oxygen dissociation curve with respect to oxygen carrying capacity. So let's measure. So when we have the concentration of oxygen in blood, so these are the different concentrations of oxygen in blood. Here you are going to have let's say that you have 150 grams per liter of all that. Here you are going to have the concentration of oxygen with respect to the partial pressure of oxygen. So you need to know that if you have your hemoglobin level of 100 grams per liter, you are going to have a certain oxygen concentration of less than 6 millimoles per liter of blood. So you are going to have a oxygen concentration of less than 6 millimoles per liter of blood. The more you increase the hemoglobin level, the more the oxygen capacity of blood, because more of oxygen are going to be stored inside the red blood cells. They are going to be stored inside the hemoglobin, found inside the red blood cells. So that's why you have an up and down rise of the level of oxygen. But now let's see the oxygen dissociation curve associated with saturation. We need to know that according to Bohr model, the Bohr equation, you need to know that when you have a decreased level of carbon dioxide, a decreased temperature, an increased pH, and you have a decreased level of diphosphoroglycerate, you are going to have the shift of the oxygen dissociation curve to the left. So this occurs usually inside the lungs. So this shift of oxygen dissociation curve to the lungs occurs inside the lung. And what is the significance of this shift of oxygen dissociation curve? So you see that as the oxygen dissociation curve shifts to the left, it makes the body to be highly absorbing oxygen with a minimal amount of partial pressure of oxygen. So you see that inside the lungs, the oxygen dissociation curve shifts to the left. So for a small amount of partial pressure of oxygen, we are going to have a high saturation of the hemoglobin. Now, inside the tissue, what happens is that at the tissue, you mostly have increased level of carbon dioxide, increased temperature, decreased pH, and diphosphoroglycerate. You need to know that diphosphoroglycerate is a product of anaerobic respiration and is usually found inside the red blood cells. You need to know that red blood cells do not do Krebs cycle. They only stop at the level of glycolysis, and thus they produce diphosphoroglycerate. So now, that when you have the shift of the curve to the right at the level of the tissues, what happens is that as you have this shift to the right, you need to know that much more pressure of oxygen should be required in order to place oxygen inside the red blood cell. So in this case, oxygen is going to mostly diffuse from the red blood cell into the tissue as you move away from the lungs. So now these are oxygen dissociation curve for the different molecules. So you have oxyhemoglobin. You see that myoglobin is going to have a higher oxygen dissociation curve. Fetal hemoglobin is going to have a higher oxygen dissociation curve compared to adult hemoglobin. So, and this is because you need to know that all of the oxygen of the fetus come from the mother. So the hemoglobin of the fetus should be much more affinitive to oxygen compared to the mother's hemoglobin. So we have visualized everything involved with respiration. So we say thanks for your kind attention. Please don't forget to like and subscribe for our channel. Thank you.